All right, so yesterday we got our introduction into carbohydrates. We said that there's two main classes of carbohydrates. One are aldoses. Those always have the aldehyde coming off the top in the open chain form. And then ketoses, where you've got a ketone off the top. In addition to that, we said that all natural sugars are D sugars, which means that bottom OH is always going to be sticking to the right in the Fisher representation form. And you can use that to determine how many natural stereoisomers on here. I think I confused a few people too, where they thought that this position down here, let me highlight it in yellow, is not a stereocenter. It is. It's just in nature, it exists only with the OH coming off the right-hand side. So it's always going to be the same stereocenter. If we go down, we saw that Fisher projections are showing up again. You got to remember the bow tie rule, that the horizontal crossbars are pointed out towards you and the vertical portion is curving away from you. And that sugars, just like any sort of aldehyde and ketone, can exist in the open chain form or a hemiacetal form. So we went through and we briefly saw this mechanism as review. And then we went over some definitions. So we said when they zip themselves up into a ring system, you can get anomers, meaning you can scramble the stereocenter off that green carbon. And we said that biologists oftentimes like to show this as a Haworth projection, where it looks like vertical lines going up and down rather than true axial and equatorial substituents. And then we went over a few basic definitions, but for the most part, that's where we ended. Today, what we're going to do is look at the reactivity of carbohydrates, specifically the reactivity of monosaccharides. So first thing we're going to start with is a bit of review. And this is acylation. So with acylation, you typically will react your aldehyde in the closed chain form, so it's going to be a hemiacetal, with an acylating agent. So in this one, I'm just going to draw D-glucose. Is this alpha or beta D-glucose? Beta, and we know that because this group is in the equatorial position. If it were axial, then it would be alpha. So this is beta D-glucose, and we need to acylate this. And if you remember, an acyl group looks like this, right? So we need to add on a bunch of these. What sort of reagent would be appropriate for adding on a bunch of acyl groups? Not quite. So that's our catalyst. And we saw that for Friedel-Crafts acylation. This time we don't need a catalyst.
We just need to have multiple of this, right?
Yeah, if you think about it, right, each of these groups here, all of the alcohols can act as nucleophiles. So if they can act as a nucleophile, we need some sort of electrophile to react them with that can do nucleophilic acyl substitution and give you your acyl group. So you have a couple options. One could be an acid halide, right? But that's pretty harsh. So most chemists will avoid using acid halides. Instead, what they'll use is something like acetic anhydride. And this portion right here can just be abbreviated as AC. So each of those alcohols can attack acetic anhydride. You can get an acylation reaction to occur off of all of them. And typically this is done in excess to ensure that all of those alcohols get acylated. So we can go ahead and draw our product. And I'm just going to call that OAC rather than drawing out all of those carbonyls. Does that make sense? So it's similar to our carboxylic acid derivative chapter, where we can substitute off our leaving group. In this case, it's important to remember that this is a pretty good leaving group, and why is that? Resonance, right? So when it pops off, it's a resonance stabilized anion. Okay, we can do something really similar with alkylation. So again, I'm going to stick with D-glucose. I'm going to make you get good at drawing chair structures again, whether you want to be or not. Okay, so let's take a look at the alkylation. Let me fix this a bit. And I want you to help me predict what reagent we would need to accomplish this transformation. And this time we're adding on methyl groups. So we're making a bunch of ethers. Let me move this oxygen down further into the ring. There we go. So what reagent do you think we would need in order to do this alkylation? And again, it's important to remember that these alcohols, all of them, are good nucleophiles. What was that? Close. So methoxide would also be another good nucleophile, so we need a leaving group. So what I would pick is something like methyl iodide. So methyl iodide, right? It's a good electrophile. You can attack it, do SN2 substitution, and alkylate each one of those alcohols. So you oftentimes will do this in excess. However, you do need some sort of base around in order to soak up protons, because if you think about it, we're losing all of these protons on here. So we need to have some sort of gentle base to basically absorb all of those protons without doing any other acid-base chemistry. A good gentle base is to use silver 1 oxide. And if you remember, going back to the Hoffman elimination with silver oxide, what this does is it will react with iodide, the leaving group, to form silver iodide solid. And by doing that, you precipitate out your halogen. So in this case, your iodide will precipitate out as a salt. And you generate hydroxide. And hydroxide in this case isn't produced in a large amount, but it's produced in enough where it will actually soak up all of those protons. Make sense? Typically with sugars, you want to avoid really strong acids and really strong bases, and we'll take a look at why that's the case in a second. All right, got a few more reactions. Next one is called glycoside formation. This is a much more common reaction than the first ones I showed you. But again, we're going to start with a monosaccharide. I'll just stick with D-glucose. Okay, so we've got D-glucose. And in this reaction, what we're going to do, we're going to treat this with catalytic acid, so I'll just show that as H plus in brackets, and then an alcohol, which is just going to be HOR. And let's try to predict the reaction mechanism. So if we think about it, we know we've got acid around. Acid's going to be, or acid-base chemistry is the fastest reaction in chemistry. So the first step, we're going to protonate that anomeric alcohol. And this is all under equilibrium conditions. And now, if we think about it, this is a good leaving group. It can fall off on its own, or it can be shoved off. You can show it both ways. So for example, if you want to show the shoving off route, you can show this set of lone pairs clamping down and kicking this off. And if you do that, you've now got a double bond there, whoops, and a positive charge on your oxygen. And you've got water around. That water can attack back in and do the reverse reaction if you want. But why is this so stable, this intermediate? Yeah, it's resonance stabilized. I like how you said that with hesitation. You're like, I don't know, but that's a pretty solid guess most of the time. So this is resonance stabilized. So this is quite stable. All right, if you notice, we haven't done anything with our alcohol yet. So if we still have that alcohol floating around, oops, let me keep this. This alcohol can also act as a nucleophile. So it can attack this anomeric carbon and kick up electrons to that oxygen. And this can occur at either the axial position or equatorial position. So it doesn't really matter how you show it. Sometimes what chemists will do is show it with a squiggly line to indicate that it's not clear if it's axial or equatorial. So I'll just show it with a squiggly line. And then what do you think the last step is going to be? Deprotonation, exactly. So last step, just write minus H plus in brackets, and then we'll show our final glycoside product. Yep. That's a good question. So if we go back up and we look at the top reaction, in equilibrium conditions, you could protonate any one of those alcohols. However, the other ones won't fall off, because if the other ones fall off, you get a secondary carbocation or a primary carbocation with no resonance stabilization. So it just doesn't get you anywhere in a forward direction, if that makes sense. So it does occur in equilibrium. It's just not even worth showing it because it's a dead end. Make sense? Okay. The neat thing with this is with glycosides, that this reaction can occur with any sort of nucleophile. So I'm actually going to note this. It works with amines or alcohols. If you do this with alcohols, you get an O glycoside. So over here, we call this an O glycoside, which basically just means that you reacted it with an alcohol, right? Not a nitrogen-containing compound. If you reacted it with an amine, it would be called an N-glycoside. And N-glycosides are actually pretty common. Has anybody heard of the Maillard reaction? No. So when you do cooking and you brown something or caramelize it, whether that's meat or some sort of baked good, that's actually a reaction between carbohydrates and the amines coming off of amino acids. And so you form an N-glycoside, and that gives it that unique flavor. So the browning of meats and cooking and barbecuing is due to this sort of reactivity, something most people don't think about. Yep.
So two questions. Did you say that it's N-glycoside if it's N bonded to an odd? N-odd?
Yeah, so let's write a note down here. N-glycosides form if you use an amine instead of an alcohol. Does that make sense? So the N just stands for the nitrogen and the amine.
And then also, I noticed when last year's lecture videos, you talked about it, that you have an OH coming off of an anomeric carbon. It's a reducing sugar.
Yeah, and we'll talk more about that later, but essentially when you have it in this case, it's no longer considered a reducing sugar, and we'll talk more about that later. Yep. Yeah. Yes, it can be primary or secondary. Yep, good question. In fact, amines, because they're that much more nucleophilic, they tend to occur more rapidly than the reactions with alcohols. Good question. Okay. So a glycoside is basically anything where you have a non-OH group coming off of that anomeric carbon. It could be an N-glycoside or a O-glycoside. It doesn't really matter. They're each considered glycosides. All right. So there's a few more reactions we do have to look at. Next one's called an oxidation. And I'm going to draw the Fisher projection form for this. So I'm going to write my aldehyde up here, got my alcohol down here, and we're going to do 4 crossbars. Let me zoom in a bit. Ugh. I don't like my crossbars. And we've got an OH, H, OH, OH on the right. So this is aldose. Specifically, it's D-aldose in its open chain form. And we know that it's an aldose because it's got an aldehyde on there, right? So aldehyde is always going to be some sort of aldose. And what we can do is we can react this with bromine and water. So elemental bromine and water. And you typically adjust the pH to about 6. So you run this in a buffered solution. And what do you think is going to happen to this aldehyde under oxidative conditions? What will it turn into? In fact, let me even draw out the aldehyde just so we can keep track of this. What do you think is going to happen to it? Yeah, it'll convert to a carboxylic acid, so it'll change its oxidation state. And you can change this top position into a carboxylic acid. Everything else is going to stay put. And so we first made an aldose, or we started with an aldose. The product that we get out has a carboxylic acid, so this is called an aldonic acid. So we're going to convert only that functional group. All right. Conversely, what you can do is treat this with harsher oxidizing conditions. And if you do that, you've got to use nitric acid, so HNO3, water, and heat. And if you do this, you're still going to convert that top position to a carboxylic acid, but you'll also convert primary alcohols to carboxylic acids. Let me clean this up a bit. So the lower position will also get converted to the carboxylic acid. So in this one, we oxidize this top carbon and the bottom carbon. This is called an aldaric acid. Some students have asked me, well, what if you use a stronger oxidant? Can you oxidize all of the other alcohols present? The answer is a bit complicated. It's yes, but it's completely impractical, and I'll show you why. But I gotta get some sound on here. It's not something I could do in the room because we don't have a fume hood. Oops. So this is
What's going on, guys? It's Bucky, and welcome to the third episode of
This is a reaction of sugar, which is a carbohydrate with a strong oxidant. But let me see if I can find the spot. Might have to fast forward. Okay, so what he's going to do is he's just going to react sulfuric acid, really strong oxidant, with just standard table sugar, and we'll see what happens.
So you want to add just enough so it saturates all the sugar. And at first, it's
not going to be saturated, so that's why you need your glass stir rod. So go ahead and take note of the color of this reaction. It's going to start out as kind of tan, and then as you can see, as I'm stirring it, parts of it turn black and parts of it are getting more dark brown. And even though you can't feel it or smell it, it kind of smells like, well, burnt sugar. And there's a lot of heat coming off this right now. It's getting really warm. So I'm going to go ahead and stir this. And as you can see, basically now it's really dark brown, almost black. And that's what we want. So right now it's getting really hot. I can hardly keep my fingers on there anymore. And that's why I got these tongs right here. So I can go ahead and handle it. Move this a little bit closer. Now let's just go ahead and make sure that this is moved away.
So that pretty much shows that if you try to do some of the stronger oxidizing reactions that we've seen in class that require sulfuric acid, you get this runaway reaction where everything wants to oxidize all at once, which basically causes thermal decomposition of your product, and you get these like snake-looking things coming out. You can do this with gummy bears too. It's pretty fun.
Oh yeah.
Yep.
So can two like reagents be characterized as two things? Like because sulfuric acid is an acid, but it can be an oxidant too.
Yeah, it can be both. Quite often, strong acids are also strong oxidants. Yeah. In this case, they didn't even use the whole chromic acid mixture. They just used sulfuric acid, and even then it ran away. So the practicality of oxidizing all of the remaining secondary alcohols just isn't going to happen. You won't get anything good out of it besides black charcoal or that snake-looking thing. So it's just not typically done. Does that make sense? All right. So now we've got to look at something called reducing sugars versus non-reducing sugars. And you might run into this in biology a lot. There's a lot of classic tests that can be done, and I'll show you one of those in a minute. But let's start with our standard D-glucose. Clean this up. All right, reducing sugars always have an alcohol coming off of the anomeric carbon. And let's take a look at why they're called reducing sugars. It's important to remember that sugars can exist in their closed chain and open chain form. So let's open this up into the open chain form. So for D-glucose in the open chain form, I'll draw it in the Fisher representation rather than bond line notation. We'll look at the open chain form, so we know that D-glucose is an aldose. It's got an aldehyde on the top. And that you can oxidize either one of these positions. So you can oxidize and you can oxidize, right? We just saw that in the previous reactions. So if glucose is oxidized, it is acting as a reducing agent, right? So this is going way back to Gen Chem and even Chem 110, I think we talked about this. So if glucose is oxidized, it is acting as a reducing agent. That's why they're referred to as reducing sugars, is if you're capable of ring opening it into an aldehyde form and then oxidizing that, it's acting as a reducing agent. Does that make sense? I'll show you a cool video, but before we do, I want to show you a little bit of the chemistry behind this. There's a really neat test called the Tollans Test. And it's actually how they used to make mirrors before mass production of mirrors became prominent. And the idea behind the Tollans test was you take an aldehyde, so for example, glucose can ring open to its aldose form with the aldehyde on the top. And you can react this with silver cations. And in this case, silver wants to steal electrons, right? So silver is going to steal electrons and become silver solid. And during this process, we're going to oxidize the aldehyde to a carboxylic acid. So it's important to remember in this situation, it's losing electrons. Therefore, it's oxidized. It's transferring them to the silver, right? Because the silver in this case must be gaining electrons. All right, so what people used to do is they would mix sugar with silver cations. They would shake it up. The silver cations would plate out as silver solid. And I'll show you this cool video of this being done in a lab setting. Hopefully this will work.
Solid. Right, I'm going to start off with a flask that contains a solution of silver nitrate, and I'm going to add a little bit of ammonia. And when I add the ammonia, you see that it's forming a sort of brown colour. I'm going to keep on adding the ammonia. In a minute, that brown colour has disappeared, and that's disappeared, isn't it? Now what I'm going to do is to add some sodium hydroxide. That's now formed a sort of very dark brown, almost a black material. So now I'm going to add more ammonia. And again, I'm going to add ammonia until the liquid goes back to being colourless. Let's take a moment or two. There we go. And then finally, I'm going to add some glucose. So there's the glucose. I'm going to put the lid on, put a clip on. I'm going to give it to you, Dylan. I want you to hold that. And I want you to give it a really good shake. That's it, really hard shake, that's good. That's it, keep shaking. That's it. So what's happening inside this flask now is there is a chemical reaction taking place, and it's forming a solid. The actual material that it's forming is silver. We're making pure silver metal. Keep shaking. It takes about 3/4 of an hour, is that okay? It does actually take a minute or two, but the harder you shake, the better it works, so keep shaking, don't drop it though. Okay. So metal, silver metal is being formed sort of atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in colour. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the flask. And as they build up, we should see silver metal in the form of a mirror building up on the inside of the flask. And you're all seeing those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. Little balls of glass, and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, so have a quick look. Almost there, keep going a little bit longer. Still looking a little bit dark. Excellent. All right, give it back to you then. Right, I'm going to take the clip off. Take out the stopper. Just wash that off. And I'm going to pour out the remaining chemicals. And then I'm going to rinse this out with distilled water. Rinse it out a second time. Rinse back third time. There we go. Look at that on, dry this off. Flip back on. And if you want to just give a little polish, there you go. If you like to hold it up by the neck, that's it. If you bring a camera in, you have a look at this, and we've got a lovely silver mirror. There we go.
All right, so that's the Tollans test. It's pretty fun to do. I remember when I was a student, I used to smuggle glassware out of the lab just because I thought it looked cool and it had silver in it. But yeah, it's a really quick, simple test to see if you have a reducing sugar. What do you think happens if you have a glycoside? It won't do a thing, right? You have to have that alcohol coming off the anomeric carbon for this sort of chemistry to work. So it won't work if you've got some sort of glycoside. So that's a really quick, simple test to tell if you've got a glycoside. All right, does that make sense? So those are the basic reactions of carbohydrates. Most carbohydrates nowadays, you just buy bottles of them from Sigma Aldrich or somewhere online. But prior to that, they actually built their own carbohydrates. So we'll look at some old school chemistry. And this involves the chain lengthening and shortening of various carbohydrates. And we'll start off with lengthening. And the lengthening reactions were done by two chemists, Kalani and Fischer. And you might remember the name Fischer, right? Fischer representation, Fischer projections. He was the pioneer of carbohydrate chemistry, so he was the one that actually helped determine the absolute stereochemistry of most natural carbohydrates. And I'll show you some of the chemistry he did. All right, the overall reaction is pretty straightforward, and I'm not going to draw the whole Fischer projection. I'm just going to show a basic aldehyde with an R group. You can imagine that R group is the tail of the Fischer representation. And apparently he was very brave. So he was working with cyanide. And by doing this, what do you think is going to happen? So let's go ahead and actually draw out the bond line structure for this. And try to rationalize the chemistry. So first step, we can steal a proton. If you're not dead before that step happens. And then your cyanide can attack in, kick up electrons to that oxygen. And now you've got two different possible products. Just let me clean this up a bit. You've got one with the alcohol off the right-hand side, plus one where the alcohol is coming off the left-hand side. Does anybody remember the name of this functional group when cyanide anion attacks into an aldehyde? We saw it a while ago, but these are called cyanohydrins. And you end up with two of them. They differ at one stereocenter, not the rest of them. So what do we call that if you've got two sugars that differ at one stereocenter but not at the anomeric carbon? What do you think?
Wait, are you sure it's HOH and HOR or HO?
Oh, sorry, this should be an H. Thank you. So what do we call diastereomers that differ at one stereocenter that's not the anomeric carbon? This was yesterday. What was that? Epimers, exactly. So in this case, we're making a pair of epimers. Okay, so after this step, what you can do is treat it using some reducing conditions. So what I'm going to do is draw my arrow going this way, and they used hydrogen gas, then a special palladium barium sulfate catalyst. And they were actually able to reduce the triple bond between the carbon and the nitrogen to a single bond. Or to a double bond, excuse me. Did I say single bond? Shoot. All right. I stand corrected. So you're still going to end up with a pair of epimers out. What are these functional groups called? That we just made? They're no longer nitriles or cyanohydrins. What do we call a carbon-nitrogen double bond like that? Oh man. Come on, guys. Imines, exactly. It's not an enamine, right? We don't have a carbon-carbon double bond. We have a carbon-nitrogen double bond. So this is a pair of imines. They're still epimers, right? Because they do differ at only one stereocenter. And then what happens with imines if we flood them with water? What will they convert back into? Not an OH. How did we make imines previously? Yeah, we made them with an aldehyde or a ketone, right? So if we flood this with water, it should go back to an aldehyde or ketone. Do you think it's going to make an aldehyde or a ketone? Aldehyde, right? So essentially what's going to happen here is this whole group is going to get converted to a CO double bond, right? Okay, so let's draw both of our products that we would get out. Now we've got an aldose with an extra carbon, right? Because if we look back at our original aldose up here, we can even label it as an aldose if we want. You see how the top aldose, we just have that carbonyl group. The bottom one, we gained a carbon in this overall reaction. So he was using this to basically add carbon groups one by one to carbohydrates. The problem was he was always getting two different products out. So he got pretty clever, and he was actually able to do a lot of optical rotation studies on these to differentiate which was which. And he was able to do that by essentially looking at meso compounds. Do meso compounds rotate plane polarized light? No, they don't. So he was trying to use all these tricks with optical rotation to basically separate and isolate these. The nice thing with these, right, is these are epimers. Epimers are also diastereomers. Right, so they're just a special type of diastereomer. Can we easily separate these? Yeah, we can. If you remember, enantiomers are the ones that are really challenging to separate because they have the exact same physical properties. These ones have very different physical properties, so you can separate them a lot easier. So they're relatively easy to purify or separate. So that was one of the tricks that Fisher used during his studies of carbohydrates. All right, he also did the reverse reaction where he was trying to lop off carbons one by one to study the behavior of carbohydrates. So let's take a look at that next. And this is called the wool degradation. And the wool degradation is basically the reverse reaction of what we just saw. So I'll go ahead and draw the overall reaction first, and then we'll take a look at it. So I'm just going to pick one of the aldoses that we previously made. And in this reaction, first thing we're going to do is treat it with an amine nucleophile. And if you remember, we're going to get this unique type of imine out. What do we call an imine that has an OH coming off of it? I haven't seen this in a while. This is called an oxime. I know there's a lot of weird functional group names, but it's just a special type of imine. And why does the nitrogen attack the aldehyde and not the oxygen? Yeah, it's a better nucleophile, exactly. So we're going to get this oxime. And then in the next step, after we've formed that, we're going to create or treat this with acetic anhydride. And sodium acetate and acetic acid. So a big mixture of all of these things. And what we're going to do is we're going to swap off that OH for an acyl group. Or actually react the OH to form an acyl group, I should say. Okay, so now we've done our acylation of the alcohol on the oxime. Now we've still got base around. Got our sodium acetate. All right, this base can then grab this proton, and then what we're going to do is clamp down and then kick off our acyl group. The whole reason that we did this was that this is a good leaving group. Just like we saw before, it's resonance stabilized. It's easier to kick off than if it were just a pure alcohol. Okay, so we're making progress. Now we've got a carbon-nitrogen triple bond. Oops. Come on. And what was this called again? We just went over that name. Cyanohydrin. So we've gone right back to the intermediate we saw before. And what I'm going to do is I'm actually going to show this as an OH single bond. And in the last step, we're going to treat this with a strong alkoxide base. So something like sodium methoxide would work well. I'm going to grab this proton, clamp down, and eject off cyanide. Okay, so now we've got an aldehyde here, and we lost cyanide as a leaving group. Essentially what happens is cyanide is kicked off, and in that process, you lost a carbon. The nice thing with doing the shortening reaction versus the lengthening reaction is you don't run into that problem of making epimers, right? So in this case, we're only getting one product. So quite often they did both reactions on carbohydrates and then tried to pair up the ones with similar physical properties, similar optical rotations, and they could narrow down the identity of a particular carbohydrate. Does that make sense? All right, I think we're going to stop before we get into polymers, but one thing I did want to do is take a look at the pod. Today's pod is about a reaction with D-glucose, and if we look at this, what I would recommend doing is try to start out with D-glucose in its normal chair conformation, and then figure out how to make a glycoside to form one of these two views. They're the exact same molecule, so you can show them a few different ways, but essentially what this pod is about is a natural glycoside that's formed when glucose is burned. So they can use this to actually track the smoke from forest fires. It's pretty interesting. So they can see how far the smoke goes by looking for these molecules. Make sense? All right. If you have any problems with this too, I'll be in my office tomorrow, but I would encourage you to try to work with some classmates to see if you can figure it out.